Welcome friends. In this module we discuss numerical solutions for ordinary differential equations, boundary value problems and eigenvalue problems. A second order differential equation must have two conditions for its numerical solution. If these conditions are given at the start, then the problem is an initial value problem. In this session, we consider the case when the conditions may be at different points, usually at the end points of the region of interest, and such problems are called boundary value problems. We first discuss exact solution and then discuss numerical solution of boundary value problems. We will see that finite difference method is very useful in finding the solution of boundary value problems. Richardson's extrapolation formula also will be discussed. Eigenvalue problems, in particular Sturm-Liouville's problem, will be discussed. Both exact and numerical solutions of such problems will be discussed. Boundary value problems. Since the general solution to a second order differential equation y double dash plus p of x into y dash plus q of x into y equal to g of x, let it be 1, contains two arbitrary constants, we need two conditions for obtaining a particular solution. Sometimes the two conditions are of the type y of alpha equal to y0, y of beta equal to y1, let it be 2. The conditions in 2 are called boundary conditions since they refer to the boundary points alpha, beta of an interval I. Equation 1 and condition in 2 together constitute what is known as a boundary value problem. If the function g has the value 0 for each x and if the boundary values y0 and y1 are also 0, then the problem 1 with conditions 2 is called homogeneous. Otherwise, the problem is non-homogeneous. Remark: sometimes the boundary conditions have the form a0 y of alpha plus a1 y dash of alpha equal to c1 and b0 y of beta plus b1 y dash of beta equal to c2. Problem 1. Solve the boundary value problem y double dash plus 2y equal to 0, y at 0 equal to 1, y at pi equal to 0. Solution. The general solution to the given differential equation is y equal to c1 cos root of 2x plus c2 sin root of 2x. Using the first of boundary conditions, we obtain y of 0 equal to c1, that is equal to 1. The second boundary condition implies that c1 cos root of 2 pi plus c2 sin root of 2 pi equal to 0. So, c2 equal to minus cot root of 2 pi. Thus, the solution of the given boundary value problem is y equal to cos root of 2x minus cot root of 2 pi into sin root of 2x. Problem 2. Solve the boundary value problem y double dash plus 2y equal to 0, y at 0 equal to 0, y at pi equal to 0. Solution. The general solution is given by y equal to c1 cos root 2x plus c2 sin root 2x. The first boundary condition requires that c1 equal to 0. The second boundary condition gives c2 sin root 2 pi equal to 0. Since sin root 2 pi not equal to 0, we must have c2 equal to 0. Consequently, y equal to 0 for all x is the only solution of the given boundary value problem. This example illustrates that a homogeneous boundary value problem may have only the trivial solution y equal to 0. Problem 3. Solve the boundary value problem y double dash plus y equal to 0, y at 0 equal to 0, y at pi equal to 0. Solution. The general solution is given by y equal to c1 cos x plus c2 sin x. The first boundary condition requires that c1 equal to 0. The second boundary condition is also satisfied when c1 equal to 0 regardless the value of c2. Thus, the solution of the given boundary value problem is y equal to c2 sin x, where c2 is still arbitrary. This example illustrates that a homogeneous boundary value problem may have infinitely many solutions. Problem 4. Solve y double dash plus y equal to 0, y at 0 equal to 1, y at pi equal to a. Solution. The general solution is given by y equal to c1 cos x plus c2 sin x. Using the first of the boundary conditions, we have y at 0 equal to c1, that is equal to 1. The second boundary condition gives y at pi equal to minus c1, that is equal to a. These two conditions on c1 are incompatible if a not equal to minus 1. So, the problem has no solution in that case. However, if a equal to minus 1, then both boundary conditions are satisfied, provided that C1 equal to 1, where C2 is still arbitrary. In this case, a solution to the given boundary value problem is y equal to 3 cos x plus C2 sin x, where C2 is still arbitrary. This example illustrates that a homogeneous boundary value problem may have no solution, and also that under special circumstances it may have infinitely many solutions. Numerical solution of boundary value problems. We consider the boundary value problem y double dash plus p of x into y dash plus q of x into y equal to g of x, let it be 3, with the boundary conditions y at x 0 equal to a, y at x n equal to b, let it be 4. If u of x is any solution of the equation 3 which satisfies the condition u at x 0 equal to a, and v of x is any non-trivial solution of the equation y double dash plus p of x into y dash plus q of x into y equal to 0 which satisfies the condition v at x 0 equal to 0, then the function y of x equal to u of x plus a into v of x satisfies 3, and the condition y at x 0 equal to a for any constant value of a. Further, if p, q and g are continuous on the interval x 0 x n, then a solution to the given boundary value problem is found if a can be determined such that u of x n plus a into v of x n equal to b. Problem 5. Solve the boundary value problem y double dash equal to x y plus x square, y at 0 equal to 0, y at 1 equal to 1. Solution. A particular solution to the given differential equation is y equal to minus x. Hence, we put y equal to minus x plus a into v of x, where v equal to 0 at the origin. Using Picard's method, v of x equal to x plus 2x raised to 4 by 4 factorial plus 2 into 5x raised to 7 by 7 factorial plus 2 into 5 into 8x raised to 10 by 10 factorial plus etc. Now, using the boundary condition y at 1 equal to 1, y equal to minus x plus a into x plus 2x raised to 4 by 4 factorial plus 2 into 5 into x raised to 7 by 7 factorial plus 2 into 5 into 8 into x raised to 10 by 10 factorial plus etc. gives a equal to 2 divided by 1 plus 1 by 12 plus 1 by 504 plus etc. that is equal to 1.84274. We now describe finite difference method. Finite difference method. We consider the boundary value problem y double dash plus p of x into y dash plus q of x into y equal to g of x with the boundary conditions y at x 0 equal to a, y at x n equal to b. The finite difference method for the solution of a boundary value problem consists in replacing the derivatives occurring in the differential equation and the boundary conditions by means of their finite difference approximations, and then solving the resulting linear system of equations. The finite difference approximations to the derivatives are obtained as follows. The Taylor series representation of y at x plus h is given by y at x plus h equal to y of x plus h into y dash of x plus h square by 2 factorial into y double dash of x plus etc., which gives y dash of x equal to y at x plus h minus y at x divided by h plus terms involving powers of h. The above is the forward difference approximation for y dash of x. Similarly, y at x minus h equal to y of x minus h into y dash x plus h square by 2 factorial into y double dash of x minus etc., which gives y dash of x equal to y at x minus y at x minus h by h plus terms involving powers of h. The above is the backward difference approximation for y dash of x. Also, y at x plus h minus y at x minus h equal to y of x plus h into y dash of x plus h square by 2 factorial into y double dash of x plus etc. minus of y of x minus h into y dash of x plus h square by 2 factorial into y double dash of x minus etc., which gives y dash of x equal to y at x plus h minus y at x minus h all divided by 2h plus terms involving powers of h square, let it be 5. The above is the central difference approximation for y dash of x. Also, y of x plus h plus y of x minus h equal to y of x plus h into y dash of x plus h square by 2 factorial into y double dash of x plus etc. plus y of x minus h into y dash of x plus h square by 2 factorial into y double dash of x minus etc., which gives y double dash of x equal to y at x minus h minus 2 into y of x plus y at x plus h by h square plus terms involving powers of h square, let it be 6. To solve the boundary value problem given by equations 3 and 4, we divide the range x0 xn into n equal sub-intervals of width h, so that xi equal to x0 plus I into h for I equal to 1, 2, etc. n. The corresponding values of y at these points are denoted by yi equal to y at xi, that is equal to y of x0 plus I into h for I equal to 0, 1, 2, etc. n. Using equations 5 and 6, values of y dash of x and y double dash of x at the point x equal to xi are given by yi dash equal to yi plus 1 minus yi minus 1 all divided by 2h plus terms involving powers of h square, and yi double dash equal to yi minus 1 minus 2yi plus yi plus 1 divided by h square plus terms involving powers of h square. At the point x equal to xi, the differential equation 3 gives yi double dash plus pi into yi dash plus qi into yi equal to gi, where pi equal to p of xi, qi equal to q of xi, gi equal to g of xi, yi equal to y of xi. Substituting the expressions for yi dash and yi double dash, the above equation gives yi minus 1 minus 2yi plus yi plus 1 divided by h square plus pi into yi plus 1 minus yi minus 1 divided by 2h plus qi into yi equal to gi for I equal to 1, 2, etc. n minus 1, let it be 7, where y0 equal to y at x0, that is equal to a, and yn equal to y at xn, that is equal to b. The above can be simplified to the following form: 1 minus h by 2 into pi into yi minus 1 plus minus 2 plus qi into h square into yi plus 1 plus h by 2 into pi into yi plus 1, that is equal to gi into h square for I equal to 1, 2, etc. n minus 1. The above gives the following algebraic system of n minus 1 equations: 1 minus h by 2 into p1 into y0 plus minus 2 plus q1 into h square into y1 plus 1 plus h by 2 into p1 into y2 equal to g1 h square, 1 minus h by 2 into p2 into y1 plus minus 2 plus q2 into h square into y2 plus 1 plus h by 2 into p2 into y3, that is equal to g2 h square, etc. 1 minus h by 2 into pn minus 1 into yn minus 2 plus minus 2 plus qn minus 1 h square into yn minus 1 plus 1 plus h by 2 into pn minus 1 into yn, that is equal to gn minus 1 h square. Since y0 equal to a and yn equal to b are already known, the above system of equations may be solved for the n minus 1 unknowns y1, y2, etc. yn minus 1. Problem 6. Number 1. Using numerical methods with step size h equal to 1 by 2 and h equal to 1 by 4, and number 2. Using exact method, find the value of y at 0.5 to the following boundary value problem: y double dash plus y plus 1 equal to 0 with the boundary conditions y at 0 equal to 0, y at 1 equal to 0. Solution. Comparing with the standard equation 3, we have p equal to 0, q equal to 1, g equal to minus 1, and hence using equation 7, the finite difference approximation for the given second order differential equation is yi minus 1 minus 2yi plus yi plus 1 divided by h square plus yi plus 1 equal to 0 for I equal to 1, 2, etc. n minus 1. On simplification, yi minus 1 plus h square minus 2 into yi plus yi plus 1 equal to minus h square for I equal to 1, 2, etc. n minus 1. The boundary conditions are y0 equal to y at x0, that is equal to y at 0, that is equal to 0, yn equal to y at xn, that is equal to y at 1, that is equal to 0. The above equations give a system of n plus 1 equations in n plus 1 unknowns with y0, y1, etc. yn. If we set h equal to 1 by 2, then n equal to 2, then the corresponding system of 3 equations in 3 unknowns is y0 plus 1 by 4 minus 2 into y1 plus y2 that is equal to minus 1 by 4 with y0 equal to 0 and y2 equal to 0. Hence, 7 by 4 y1 equal to y0 plus y2 plus 1 by 4 that is equal to 1 by 4 or y1 equal to 1 by 7. Hence, y at 0.5 equal to y1 that is equal to 1 by 7 that is 0.14285. If we set h equal to 1 by 4 then n equal to 4. The corresponding system of 5 equations in the 5 unknowns is y0 minus 31 by 16 y1 plus y2 that is equal to minus 1 by 16, y1 minus 31 by 16 y2 plus y3 equal to minus 1 by 16, y2 minus 31 by 16 y3 plus y4 equal to minus 1 by 16 with y0 equal to 0 and y4 equal to 0. Solving the above system, we obtain y2 equal to 63 divided by 449. Hence, y at 0.5 equal to y2 that is equal to 63 by 449 that is equal to 0.14031. Now, to find the exact value, we proceed as follows. The characteristic equation associated with the given differential equation y double dash plus y that is equal to minus 1 is lambda square plus 1 equal to 0, which gives lambda equal to plus or minus I. Hence, the solution to the homogeneous equation y double dash plus y equal to 0 is y equal to a cos x plus b sin x. Also, y equal to minus 1 is a particular solution to the differential equation y double dash plus y equal to minus 1. Hence, the general solution to the given differential equation y equal to a cos x plus b sin x minus 1 using the boundary conditions y at 0 equal to 0, y at 1 equal to 0, we obtain a minus 1 equal to 0 and a cos 1 plus b sin 1 minus 1 equal to 0. Hence, the solution to the given boundary value problem is y equal to cos x plus 1 minus cos 1 into sin x divided by sin 1 minus 1. Hence, the exact value of y at 0.5 is y equal to cos 0.5 plus 1 minus cos 1 by sin 1 into sin 0.5 minus 1 that is equal to 0.139493927. Richardson's extrapolation formula. In order to improve the accuracy of the solution of a boundary value problem, we use Richardson's extrapolation formula. Let y1 and y2 be two approximate values of y obtained using finite difference method with the step sizes h1 and h2 respectively. Then y minus y1 equal to a into h1 raised to n and y minus y2 equal to a into h2 raised to n. Eliminating a between the above two equations, we obtain y equal to y2 h1 raised to n minus y1 h2 raised to n divided by h1 raised to n minus h2 raised to n. If we take h1 equal to 2 h2 and n equal to 2, then the above takes the form y equal to 4 y2 minus y1 divided by 3. The above is the Richardson's extrapolation formula. Problem 7. Using Richardson's formula, find y at 0.5 to the boundary value problem y double dash plus x y dash plus y equal to 2x with the boundary conditions y at 0 equal to 1, y at 1 equal to 0. Solution. Using equation 7, the finite difference approximation of the given differential equation is y I minus 1 minus 2 y I plus y I plus 1 all divided by h square plus x I into y I plus 1 minus y I minus 1 divided by 2h plus y I equal to 2 x I for I equal to 1, 2, etc. n minus 1. On simplification, the above gives 2 minus h x I into y I minus 1 plus 2 h square minus 4 into y I plus 2 plus h x I into y I plus 1 equal to 4 h square x I for I equal to 1, 2, etc. n minus 1. Let it be 8. Let h equal to 1 by 2, then n equal to 2, and in this case we have x0 equal to 0, x1 equal to x0 plus h that is equal to 1 by 2, x2 equal to x0 plus 2h that is equal to 1, y0 equal to y at x0 that is equal to y at 0 that is 1, y2 equal to y at x2 that is equal to y at 1 that is 0. Substituting these values in equation 8 with I equal to 1, we obtain 2 minus 1 by 2 into 1 by 2 into 1 plus 2 into 1 by 2 all square minus 4 into y1 plus 2 plus 1 by 2 into 1 by 2 into 0 that is equal to 1 by 2. which gives y1 equal to y at x1, that is equal to y at 0.5 equal to 0.35714. Next, we let h equal to 1 by 4, then n equal to 4, and in this case we have the following system of equations: minus 62 y1 plus 33 y2 equal to minus 30, 15 y1 minus 31 y2 plus 17 y3 equal to 1, 29 y2 minus 62 y3 equal to 3, with y0 equal to 1 and y4 equal to 0. Solving the above system, we obtain y2 equal to y at 0.5, that is equal to 0.36081. Taking y1 equal to 0.35714 and y2 equal to 0.36081, and using the Richardson's formula, y at 0.5 equal to 4 into 0.36081 minus 0.35714 or divided by 3, that is 0.36203. Eigenvalue problems. Consider the boundary value problem y double dash plus lambda y equal to 0. Let it be 9 with the boundary conditions y at 0 equal to 0, y at pi equal to 0. Let it be 10. We define eigenvalues and eigenfunctions as follows. Definition: the value of lambda for which non-trivial solutions of 9 and 10 occur are called eigenvalues, and the corresponding non-trivial solutions are called eigenfunctions. Problem 8. Discuss whether lambda equal to 1 is an eigenvalue of the boundary value problem 9 and 10. Give some eigenfunctions. Is lambda equal to 2 an eigenvalue? Solution: observe that the above boundary value problem 9 and 10 is the same as that in problems 2 and 3 if lambda equal to 2 and lambda equal to 1 respectively. Referring to problem 3, we note that for lambda equal to 1, equations 9 and 10 have the solution y equal to C2 sin x, where C2 is an arbitrary constant. This shows that for lambda equal to 1, equations 9 and 10 have non-trivial solutions. Hence, lambda equal to 1 is an eigenvalue. Any non-zero multiple of sin x is an eigenfunction corresponding the eigenvalue lambda equal to 1. Referring to problem 2, we note that for lambda equal to 2, equations 9 and 10 have only the trivial solution y equal to 0. Hence, lambda equal to 2 is not an eigenvalue. Sturm-Liouville's problem. Sometimes a second order differential equation is written in the form d by dx of p of x into dy by dx minus q of x into y plus lambda into rho of x into y equal to 0. Let it be 11. The problem of solving this equation with respect to the boundary conditions alpha 0 into y of a plus alpha 1 into y dash of a equal to 0 and beta 0 into y of b plus beta 1 into y dash of b equal to 0, or y at a equal to y at b, p of a into y dash of a equal to p of b into y dash of b is called the Sturm-Liouville's problem. If the interval between a and b is divided into equal parts and the derivatives are approximated by difference expressions, we obtain p r by h square into y r minus 1 minus 2 y r plus 1 plus p r dash by 2h into y r plus 1 minus y r minus 1 minus q into y r plus lambda into rho r into y r equal to 0. This can be written in the form a minus lambda I into y equal to 0, where A is a band matrix and y is a column vector. Non-trivial solution exists if determinant of A minus lambda I equal to 0, and hence the eigenvalue problem discussed now can be transformed into an algebraic eigenvalue problem. In the Sturm-Liouville case, we compute y n iteratively from d by dx of p of x into d by dx of y n, that is equal to q of x into y n minus 1 minus lambda n into rho of x y n minus 1. When integrating, we obtain two integration constants which can be determined from the boundary conditions. Also, lambda n is obtained from the condition integral from a to b y n square dx equal to 1, or from similar condition. This is illustrated in the following problem. Problem 9. Using usual method and using numerical method, find the lowest value of lambda square and the corresponding solution to the boundary value problem y double dash plus lambda square y equal to 0 for 0 less than or equal to x less than or equal to 2, y at 0 equal to y at 2 equal to 0. Solution. The general solution to the differential equation y double dash plus lambda square y equal to 0 is y equal to a cos lambda x plus b sin lambda x, and the first boundary condition gives a equal to 0, hence y equal to b sin lambda x, and the second boundary condition gives b sin 2 lambda equal to 0. Now, for the non-trivial solution b not equal to 0, so sin 2 lambda equal to 0 gives lambda equal to m into pi by 2 for m equal to 1, 2, 3, etc. Hence, the lowest value of lambda square is pi square by 4 obtained by putting m equal to 1, and the corresponding solution to the boundary value problem is y equal to sin pi by 2 into x. To obtain numerical solution, we proceed as follows. The iterative formula is y n double dash minus lambda n square into y n minus 1 for n equal to 1, 2, etc., where we find lambda n from the condition y n of 1 equal to 1. We start with y 0 equal to 2x minus x square, that fulfills y 0 at 0 equal to y 0 at 2, that is equal to 0, y 0 at 1 equal to 1. Then y 1 double dash equal to minus lambda 1 square into 2x minus x square, integrating y 1 dash equal to lambda 1 square into a minus x square plus x cube by 3. Again integrating, we obtain y 1 equal to lambda 1 square into b plus ax minus x cube by 3 plus x raised to 4 by 12. y 1 at 0 equal to 0 gives b equal to 0, y 1 at 2 equal to 0 gives a equal to 2 by 3, and y 1 at 1 equal to 1 gives lambda 1 square equal to 2.4, and hence y 1 equal to 2.4 into 2 by 3 x minus x cube by 3 plus x raised to 4 by 12, that is y 1 equal to 1 by 5 into 8x minus 4x cube plus x raised to 4. Repeating the procedure, we get the values as in the following table. The values of n are 0, 1, 2, 3 and 4. The corresponding values of y n are 2x minus x square, 1 by 5 into 8x minus 4x cube plus x raised to 4, 1 by 61 into 96x minus 40x cube plus 6x raised to 5 minus x raised to 6, 1 by 1385 into 2176x minus 896x cube plus 112x raised to 5 minus 8x raised to 7 plus x raised to 8, and 1 by 50,521 into 79360x minus 32640x cube plus 4032x raised to 5 minus 240x raised to 7 plus 10x raised to 9 minus x raised to 10, and the corresponding value of lambda n square are for 0 nil, for 1 2.4, then 2.459, 2.4664 and 2.46729. Let us summarize the session. In this session, we have seen that the finite difference method is systematic and dynamic in producing solution to boundary value problem. The resulting technique led to system of linear equations which can be solved by any available methods used for solving such system. Richardson's extrapolation formula have been discussed. Eigenvalue problems, in particular Sturm-Liouville's problem, have been discussed. Both exact and numerical solutions of such problems have been considered. Before moving to the next session, try to answer the following questions. Question 1. Using numerical method, solve the boundary value problem y double dash equal to x plus y with the boundary conditions y at 0 equal to y at 1 equal to 0. Number 2. The differential equation y double dash plus lambda xy equal to 0 is given together with the boundary conditions y at 0 equal to 0, y at 1 equal to 0. Find the smallest eigenvalue lambda by approximating the second derivative with the second difference for x equal to 1 by 4, 1 by 2 and 3 by 4. Question 3. Find all the eigenvalues and eigenfunctions of the boundary value problem y double dash plus lambda y equal to 0, y at 0 equal to 0, y at pi equal to 0. Number 4. Find all the eigenvalues and eigenfunctions of the boundary value problem y double dash plus lambda y equal to 0 with the boundary conditions y at 0 equal to 0, y at L equal to 0. Number 5. Find the smallest eigenvalue of the differential equation x y double dash plus y dash plus lambda x y equal to 0 with the boundary conditions y at 0 equal to 0, y at 1 equal to 0. The books for your reference are R.Y. Rubinstein, Simulation and the Monte Carlo Method, John Wiley, 1981. D.J. Yakowitz, Computational Probability and Simulation, 2nd edition, Wesley, 1977. Hope you enjoyed this session. See you next time. Until then, goodbye.